Good afternoon, and many thanks to all of you to be here. It's a great pleasure for me to open this series of online lectures devoted to pure mathematics. The conferences will be held by leading experts in different branches of mathematics. More precisely, I would like to thank in advance Susanna Terracini from the University of Turin, Claudio Procesi from Sapienza University of Rome, Alessandro Berarducci from the University of Pisa, and Luigi Ambrosio from Scuola Normale Superiore of Pisa. Before to start with the scientific part of the event, let me introduce you the rector of the University of Urbino, Carlo, Professor Giorgio Calcagnini. Giorgio Calcagnini, that I want to thank you very much for his constant support. Please, Giorgio.
Thank you, Giovanni, for your presentation. It's a pleasure for me to be here with you. I hope there will be soon the chance to be all together in presence. For the moment, we have to keep carry on this kind of seminars online. For some reason, I think that it could be very useful because holding this kind of seminars by means of Zoom allows many researchers to be present, to participate, even if they are so far away from Urbino that it is not easy to reach. Welcome to all the persons, the colleagues from other universities. From what I understand, this is the first seminar of this LAG seminars organization, and I would welcome, first of all, Susanna Terracini from the University of Turin. Let me thank, first of all, Giovanni for the organization of this kind of seminars. I think Raffaella is probably the other organizer of the meeting. And so thank you, Raffaella, for your support. And I think this is very important because, as you say in your webpage, that this is a very important occasion to exchange ideas with other colleagues. And this is part of what I think a university are supposed to do in order to spread ideas around the community. So thank you again, and I really hope to see you in one of the next occasions, hopefully in Urbino, and enjoy this presentation. Thank you very much, Giovanni.
Many thanks, Giorgio. Many thanks for all. Then we can start with the scientific part of the meeting. Then the first lecture of the meeting is given today by Susanna Terracini. Susanna Terracini is one of the leading experts of the Italian Mathematical School of Nonlinear Analysis. She received several prestigious prizes for her results in this field. And of course, it's impossible for me to describe here a complete and detailed bibliography. I just mentioned that very recently, she received the Schauder Medal in recognition of her outstanding development of variational methods and contribution to dynamics of differential equations, in particular for the n-body problems, nonlinear reaction diffusion equations, as well as Schrödinger equations. The official online meeting will take place just tomorrow. Then many congratulations for this prestigious prize. And again, from my part, many thanks for your kindness accepting my invitation to give this talk. Just this, please.
Well, thank you very much, Giovanni. I'm very happy to be back, albeit virtually, to Urbino, which is a beautiful town with a small but very active group of mathematicians, and which I'm very happy to be connected with. So let me share my screen. I will, okay. Here is, okay. Is it okay? Can you see the?
Yes, yes, it's okay.
The screen, the shared screen. Okay. What I'm going to share with you today is in fact a piece of linear mathematics, the linear differential equations, but maybe the way, the approach we will develop in this case is somehow close to some nonlinear analysis, and close and inspired by some nonlinear analysis. And it is related with what I will call Liouville type theorems, which are nice theorems in mathematics because they are non-existence theorems, or if you like, classification theorems. In general, the most known Liouville theorem is the one for example, for harmonic function, that says that if you have a harmonic function which is bounded, even bounded one side only, then it must be constant. So it is a non-existent theorem in the sense that states that there are no non-constant solutions of some differential equation. What I'm going to discuss here is the content, the mathematical content of some papers which have appeared rather recently that I've been authoring in collaboration with Yannick Sire, Giorgio Tortone, and Stefano Vita, with different collaboration teams. Okay, so I will consider a class of equations of a second order differential equation in a divergence form where there is a weight which is a one-dimensional weight. It is something that annihilates or explodes at a hyperplane, one codimension, one hyperplane of the space. So we will have two variables. The variable x is in general a vector variable, while y is a scalar one. And so we will consider differential operators, second order differential operators, where there is a matrix A, which depends on both variables, which is symmetric, continuous, even with respect to the variable y, and it is uniformly elliptic. And in general will be continuous, could even be Hölder continuous in some cases. And then we have this special variable y, which defines through the equation y equals 0 a hyperplane, characteristic hyperplane, which will be equivalent with respect to the matrix A in a proper sense. So in general, we will have n+1 variable, n variable called x and one called y, x scalar variable called x and one called y, and we will consider this type of equation. Okay, so it is clearly not the first time this type of equation have been considered, and let me just recall, let's say the basic and celebrated de Giorgi-Nash-Moser theorem, which for the elliptic case says that when we have a symmetric matrix with measurable coefficients satisfying a uniform ellipticity condition, then in an open set then every weak solution to the equation divergence of A of x grad u equals 0 is Hölder continuous, and there is an estimate of the Hölder's norm in a maybe smaller ball, starting from basically any estimate, L beta estimate in a bigger ball. Okay, this is a very famous and important milestone of the modern mathematics theory of differential equations. And you see, what happens is that what is missing with respect to our case is this weight that makes the equation, the coefficient of the equation, become either degenerate or singular at the characteristic hyperplane. Okay, now let me recall, let's say sorry, each time, okay. Oh, okay, now let us elaborate a little bit more and add a right-hand side to the equation. And let us state, let's say, a further theorem, which is always contained in the same theory, that says that for right-hand side that you see, I can write as a function or the divergence of a vector field. Now, if this function f or the vector field, the capital F, are sufficiently integrable, and this means for the function little f that must be of class LP1 for P1 larger than n over 2, n is the dimension, and P2, the vector field, should have coefficients, components of class LP2 with P2 larger than n, then we have the very same estimate. Okay, now there is a further step, which are the Schauder C1 alpha estimates, which are very important, and that says that if we add a further Hölder continuity assumption on the matrix A, so if we assume the coefficients of the matrix A to be of not only continuous, but of class C0 alpha, then the solutions are, the weak solution are not only Hölder continuous, but they are C1 alpha with derivatives of class C alpha, when the right-hand side again is regular enough, and regular enough means of class LP with the P larger than the dimension in the case of the forcing F, and in the case of the divergence of a field, the field itself must be of class C0 alpha. Let me just remark, this is an obvious remark, that these estimates are clearly optimal, because if you take a function, any function u of class C1 alpha and any matrix A of class C0 alpha, then you will find a solution with the right-hand side in divergence form, and the class F and the vector field F is exactly the product of A of x times grad u, and it is exactly of class C0 alpha. So Schauder estimates are very important because they are regularity estimates, but also they are compactness estimate, and can be used in various applications, also in nonlinear cases. Okay, Now, what we are adding is a weight. And we are not the first one to add these weights. These are very important, for example, in connection with fractional powers of the Laplacian or for the elliptic operators. And let me just recall that the presence of this vector of this weight does affect the regularity of solutions. Okay, for example, we have particular solutions which are of this form, u of xy. Oh, this is in the case when the matrix A is just the identity. Then we have functions which are harmonic with respect to the operator and have this form. Okay, are the power of y to the, minus a times y. Okay, and then we do have solutions which are not smooth. They might be lack continuity, lack differentiability, and so on. Okay, and so let's make a detour in the case in the theory of weighted singular degenerate elliptic operators. Okay, in general, we imagine to have a weight, and again, A will always be an elliptic, a uniformly elliptic matrix. Z is our variable, and we recall what are the main features of the weight W to build a good theory, regularity theory for the solutions. And okay, and then I have to recall one basic concept in this theory, which is the AP class, Muckenhout class. Okay, we say that a weight is of class AP. P is a positive number, is larger than 1 actually. If the averages of W of the weight on balls multiplied by this other average of this negative power of W to the power P minus 2 are bounded uniformly. Okay, so one can immediately prove that if you take a power of y, of the variable y, this will belong to the Muckenhout class AP for A larger than -1 and smaller than P minus 1. In fact, the good class for having for developing the general theory of weighted elliptic operators is the class A2, and this when we take P equal 2 implies that the exponent A belongs to the interval -1, 1. Okay, this has this Muckenhout class, the A2 Muckenhout class, has been studied in seminal papers by Fabes, Koenig, and Serapioni in the early 80s. Okay, now, okay, now let me stress that there are very good reasons to develop such theories or different theories, but now we will take a slightly different view on the problem. We will add boundary conditions at the characteristic hyperplane sigma, and we will study the solution according to Neumann or Dirichlet conditions, and we will try also to overcome the limitations of the A2 Muckenhout class in connection with these boundary conditions. And also we will take a different view in the following sense, that, well, the weight might be singular or degenerate, but we will insert it in a class of regular problems with a regularization parameter, and we will try to obtain estimates, C0 alpha or C1 alpha estimates, which are uniform with respect to this regularization parameterization. Regularization. So we will start from the papers by Fabes, Koenig, Gerson, and Serapione. There are many very important papers in the 80s, and where it is proven the elder continuity of all solutions, and we will try to overcome and elaborate more on this. Okay, now let me go back to the theory of A2 weights and go back to the original paper by Fabes, Koenig, and Serapione to see how the regularity estimate are obtained. And there are two main steps, two keys to these regularity estimates, which are the weighted Sobolev embeddings. We have for a function which are even very regular and compactly supported, there are Sobolev embeddings in appropriated in some suitable LP space for the let's say H1 for the function the connected energy, the energy related with the weight. And the second very important tool is Poincare inequality. You see that here the inequalities are written in somehow in a way which is adapted to this framework, which is halfway measure and metric space point of view. Okay, so we have these weighted Sobolev embeddings and Poincare embeddings, and then well, first with these two elements, one can prove boundedness and infinity bounds, and then the validity of the maximum principle, the unique continuation principle, Harnack inequality, and eventually from these other elements, one can prove their continuity of all energy solutions. Okay. So we start our analysis with even solution. What do we intend with the even solutions? We think of having solutions which are even with respect to the variable y, but solve in a weak sense, in an energy sense, the equation of on the full unit ball, for example. Okay, and then we understand immediately that evenness plays a role, especially when we overcome the borders of the Mukhenaup class. And let me briefly discuss this very basic example. We take the unit ball and we divide in two parts, and the hyperplane, the characteristic hyperplane cuts the unit ball in two half balls. And then we look at the function which takes the value 1 in half a ball and -1 in the other half ball. And we realize that when the exponent a is larger than 1, this jump function is an energy L-harmonic function in the full sense of being an energy LA harmonic function. And of course, we can change the value on any of the two half balls and still produce another energy solution. So not only solutions are not Hölder continuous, of course, they are not even continuous, but we see a lack of unique continuation principle. We may have two solutions which are two energy solutions which coincide in an open set, but they are not equal everywhere. Okay, so we see, in fact, the basics of the standard theory being affected by our exit from the Mukhenov class. Let me just remark, and this is again an elementary remark, that if we impose the function u to be even with respect to u, then the function will be continuous, will even be C infinity. Okay, so will be as much regular as we think. And in fact, this will be, in the end of this talk, a general result. Okay, now, in order to better understand these regularity issues in a general sense, let us regularize in an obvious way our weights. So instead of taking modulus of y to the power a, we will take an epsilon, add an epsilon square inside, and so we will have weights which are not neither exploding, neither going to infinity, nor becoming zero, vanishing close to our characteristic hyperplane. And then we try to study the associated operators in a let's say uniform way. Okay, and then we will try to perform a perturbative analysis, a singularly perturbed analysis somehow, which will give us regularity estimates in spaces C0 alpha and C1 alpha, which are uniform with respect to the parameter epsilon, up to the case epsilon equal to 0. So they will bring our estimates to the case epsilon equals 0, which is the degenerate and or singular cases. Okay, so let me. Okay, doing this this regularization entails already some little or big, technical facts. For example, it's not clear that this family of operators has a common domain. If you take as a domain the domain of the Dirichlet form, in fact, it doesn't. So one has to be a little bit careful in treating this class in a global way. Okay. Well, there is some interesting fact which relates the singular and the degenerate cases. In fact, there is a kind of duality between the two when we think of having an exponent A and a solution of some equation in the ball, then when we take the weighted derivative, this is a kind of conormal derivative of the variable W, then we find the solution of a similar equation where the exponent A has been changed into minus A. So if it was singular, it will become degenerate and vice versa. And the right-hand side will change from this form to this other form. And this will be something to keep in mind in what we are going to do. But let's proceed in a let's say gradually into this topic. Well, first let's try to elaborate, and this is let's say an easy part, given the theory of weighted Sobolev spaces and weighted Sobolev inequality, and derive as a very first and basic step Sobolev embeddings which are uniform with respect to the parameter epsilon, the regularizing parameter epsilon. This can be done, for example, okay, this if we go in the theory of weighted Sobolev spaces and inequalities as performed, for example, by Hawash, okay, the basic property is to have a measure which is deregular with respect to a measure, and this means that the measure of the ball of radius r is larger than some constant to the times the radius r to some power d. Okay, and we will say that a domain is deregular with respect to the measure if this happens. You see that this is a relation between the measure mu and the diameter of the ball. So it mixes measure and distances in our space. Okay, and then what happens is that this one can associate to our weights a dimension, which is an effective dimension, and the dimension d is equal to the true dimension times the maximum between a and 0, so the positive part of a. Okay, and the constant b can be taken independently on epsilon. This everything is uniform with respect to epsilon, and then we have Sobolev inequalities, which are in fact uniform with respect to epsilon. Okay, and the embedding, the critical exponent for the embeddings is in fact the usual critical exponent of Sobolev inequalities. Let me just remind that the true dimension is n plus 1, the effective dimension is n plus 1 plus the positive part of A. Okay, so this is 2 times the dimension over the dimension minus 2. Okay, okay, so this first analysis allows us to properly define the energy space, what is the energy space is, and to define the concept of energy solution, which is the solution with respect to the form, the Dirichlet form associated with the Sobolev space. Okay. And you can do this for right-hand side, which are weighted forcing or divergence of weighted vector fields. And this is very natural to place these problems in the energy space. And in this, the fact that A is larger is in the interval -1, 1 or exceeds, in principle, should not does not make any difference for the moment. Now let us look at our first result. We consider any power A between -1 and +infinity, and a solution which is even in Y and energy to the non-homogeneous equation in a ball, with when the function f is in some LP. And then we have two statements. One says that if the A is continuous, alpha is in the interval 0, 1, and it is below this threshold, which is in fact 2 minus the dimension, the effective dimension over P. Then we have a C0 alpha estimate. The second statement is if we think that A is also alpha continuous, and you see here we will have that P, the power P is larger than the effective dimension, then, then we have C1 alpha estimates on U. And both these properties, these estimates are epsilon stable. In what does it mean, epsilon stable? It means that they hold with constant for the whole class of regularized operators. Okay, let me stress that the evenness of the solution is extremely important, because we don't have the same estimates for all solutions. Solution must be, the evenness must enter at some point, because we know that in general energy solutions are not, well, if A is larger or equal than 1, are not even continuous. They are not C0 alpha and they are not C1 alpha. Okay, so we have this theorem, and well, we have a very similar theorem also for the right-hand sides in the divergence form. The vector field F has n+1 components, and then to get C0 alpha estimates, we just assume F, the vector field F, to be in LP with a measure, with a weighted measure, and P larger than the effective dimension. And when A is alpha Holder continuous, and F is also C0 alpha, and the last component of the vector field vanishes on the hyperplane, on the characteristic hyperplane, then we also have C1 alpha estimates. These estimates are epsilon stable, and they are, especially the second one, they are optimal. Okay, and again, the evenness of the solution enters very much in this. Okay, so how do we prove these theorems? We first regularize the problem, and we introduce the parameter epsilon, such in a way that the operators becomes uniformly elliptic when epsilon is strictly larger than 0. Then we use a scaling argument, which is, let's say, not completely new in proving Schauder estimates. These are rather classical nowadays type of arguments. And then we scale, we argue by contradiction, and we scale our variables in a way that we find in the end of this scaling argument a solution, an entire solution of some equation, which may have or not, depends on the different scaling that appear, may be reminiscent or not of the regularization. And then we prove that these solutions are, we classify all these limiting profile. And then we prove that all solutions of the singular and degenerate equations can be obtained at limits of solution to this sequence of regularizing, of a sequence of regularized problem. And then we can go beyond the C1 alpha estimates when we impose more regularity on the matrix A. And to give an example, to simplify things, we will consider for higher regularity the case when A is the identity, and we can go and obtain further regularity for even solution. We will finally obtain C infinity regularity for the solutions. Be careful, because the associated operator has not C infinity coefficients. Okay, so these are our results. Okay, and to give this higher regularity theorem, we consider, again, this case, A will be between -1 and +infinity, K is any integer, and if the right-hand side F is of class CK alpha, okay, and we consider an even energy solution to this equation, minus divergence of y to the power a of modulus of y to the power a grad u equal modulus of y to the power a f, okay, then u will be in the class ck plus 2 alpha. This is exactly the same result we would, the classical result we would have without the weight. Okay, if f is C infinity, then also u is C infinity. And this, in fact, again, is a property only of even solutions to the equation. And this can be somehow be surprising, because this, let's say, complete smoothness happens in an equation where coefficients are not as smooth as will be the solution. And again, if we turn to odd solutions, this statement is absolutely false. We have odd solutions which are not even, which are odd. And as I said before, we have a very simple solution in this case, modulus of y to the power minus a times y, which is a solution of an LA harmonic solution within the Mukataut class, and which is clearly not a C infinity function. Okay, and let me also stress that this holds for also, this result holds also outside the Mukataut class. Okay, so let me give a very, let's say, synthetic idea of how to prove this, this result. And the idea is to make an iteration, of course, for the derivatives in y. Oh, this result, once we have the previous result, you see that if we do derivatives, if we perform the derivatives with respect to the variables x, then the operator commutes, and then you can just iterate the previous result. There is nothing to do. What is difficult is to prove further regularity of the derivatives which involve the variable y, the singular variable y. And then the idea is to use this duality. Okay, so the property that solutions of the LA operator, that LA harmonic function, when you take the conormal derivative, become solution of the L minus A equation. But be careful, when you take derivatives, when you take one derivative, you apply this operator, then you change evenness in oddness. Functions which are even become odd. And the theory for odd, and there is no regularity for odd solution, as I said before. Then you have to iterate and to make somehow twice, to perform twice this weighted differentiation. And then what happens is that you can write the second derivative with respect to y as a combination of some operator. One is a double, okay, an iterated weighted derivative, and because it is iterated, will give you an even solution of another equation where you see you have the same operation on the right hand side. And then you again, here you have a singular differential operator, and you find that let's say the image of this operator, when applied to a function u, will go into another, will bring u into another equation where the coefficient, the exponent a has been increased by 2. Okay, this is why also it's very important to have a theory for all a larger than -1, because when you want to iterate these estimates and go to higher derivatives, then you have to take advantage of the regularity you have obtained for at the previous level for the an exponent a which has been increased by 2. Okay, then okay, this with some patience will work. And so let's go back. So you see, this trick allows to increase the regularity up to whatever you want. Okay, and also for all exponents between -1 and 1. What are the Liouville theorems which are involved? There is one, let's say, one big Liouville type theorem, which is the following. Okay, let's take the half plane, the half space Rn +1 plus, and let us take an exponent a which is between -infinity and 1, here you see I'm let epsilon larger or equal than 0, and let us consider a locally energy solution to this equation with the vanishing boundary condition. Okay, and assume that you have a solution which grows too slowly with respect to y, to the variable y, and z going to infinity. Z is the pair xy. Then w is identically 0. Okay. Let us forget of the weight. Okay. And let's restate this Liouville theorem in the case of the Laplacian. No weights. No. Okay. Consider a solution in the half space, a harmonic function which is identically vanishing on the boundary. Okay, and assume that this solution grows slowly than the linear growth. Okay, so it is bounded by some function z to the power gamma. Then, well, then it is 0 because the lowest possible growth for a harmonic function on a half space which is 0 on the boundary is 1. Okay, this is let's say the weighted counterpart of this theorem. Okay, and then from this theorem one can obtain a second one which applies to the powers a which are between -1 and plus infinity. Again, epsilon is larger or equal than 0. And let's take a solution, a function which is LA harmonic on the half space, and which is has 0 conormal derivative at the boundary, and grows has a growth which is less than linear. Then it is constant. Okay, this theorem again includes the theorem that you can have with a is equal to 0. So, and that says if you have a harmonic function on the half space which has 0 normal derivative at the boundary and grows less than linearly, then it is constant. Okay, and then you have a similar Liouville type theorem for the gradients, and you can say that in this very similar symmetric the very same equation, if you have a solution which has a gradient which grows less than linearly, then your solution is linear, is a linear function. Okay, this you see it is rather natural, but requires some let's say little work to be done. Okay, well, these three results are in fact the key for proving Schauder estimates by scaling. Okay, now what happens is let's now consider the case of odd solutions, so solutions which are 0 on the characteristic hyperplane, and we try to use the theory we have obtained for even solution to use the duality for to the aim of applying it to odd solution. And then in fact what happens is in the case where there is no no matrix, then if you take a solution U and you divide by this characteristic odd solution, the one we have already encountered before, then we have a solution. Okay, we have a solution of a new equation, which is changed. The exponent a is changed into 2 minus a. Now a is less than 1, it is basically negative. Okay, and again, the function f also is divided by the same function. Okay, with this in mind, we can play with oddness and evenness, and when the exponent a is between -1 and 1, then we can take any solution to the equation, to this equation, and then we can decompose the right-hand side in 2 parts, an even and an odd part, and write them in the proper way. The even part stays as it was. The odd part will be divided by the characteristic odd solution. And we assume that this even part and this weighted odd part are of class ck alpha. And then this very same regularity holds for the even and odd parts of the solutions, which are of class k is increased by 2. Okay, I'm almost, sorry, I'm done. Okay, so what happens when we have a matrix A? Well, we have to cook an odd comparison solution, which is tailored for the regularized problems and the case take into account the presence of the matrix. In general, we can do it. So we can have we can have and build this new equation, this new odd comparison solution, but then we see a new weight appearing in front of the equation. And finally, we can also deal with the case with variable coefficients. So we add one more difficulty to the problem. And I think, I'm afraid my time is over. So let me just go into at the end. Well, finally, under appropriate assumptions on the coefficient on the right-hand side, we derive again uniform in epsilon bounds, C1 alpha bounds and C0 alpha bounds. What is important is that beyond all the technicalities, the technical assumptions, and so this theorem applies to the case of curved boundaries, so can be applied to the case of characteristic manifolds which are curved, and give us Schauder estimate for the operators, the weighted operators where the weight is somehow the natural one. So it is the one where the variable y is replaced by the distance to the hyperplane sigma, which is what one expects, but it requires some work and also some smoothness, further smoothness, class 3, C3 alpha for the manifold. Okay, so thank you very much for your attention, and my time is over. Sorry for being a bit late, and thank you for your attention.
Many thanks for the nice talk. There are some questions. No questions? Remarks?
I have a curiosity.
Please.
Hello.
Ciao, Susanna. The fact that you are limited to the case alpha different from 1, if I understood well, is related to the fact that you don't have a Hardy-Poincaré inequality in that case, right?
Sorry, A is not different from 1.
Minus 1, 1.
Okay, if you
In the sense that when you are bigger than minus 1 or less than 1.
okay, the case A equal to 1 is not in the Mukhenov class.
In fact, of course.
So you cannot not apply. You don't have general C0
In fact,
the continuity of the solution.
of course.
But we do have in the range minus 1 plus infinity for even solution.
Yes, yes, but you have to stay. You cannot take minus 1.
Ah, okay. No.
Okay.
No. This is because the weight must be locally integrable itself.
Yes, of course.
Okay.
But my question is,
Sorry?
but this is related to the fact that you don't have an Hardy-Poincaré inequality, actually. This is what I was saying. But my question is, if you have your estimates.
Sorry, we don't have Hardy-Poincaré inequality in general. Because
of course.
but not only at minus 1, also we don't have in the range 1 plus infinity.
Well, you have similar ones with weights alpha, x to the alpha, x to the alpha plus 2 on the right. It always, yes, it always holds.
Sorry.
It always holds inequality of that type, except for alpha minus 1, 1.
The Sobolev, you mean? The point.
Hardy-Poincaré, how do you want to call it?
Yeah. Okay.
But my question is, since you have these stable inequalities, yes, with epsilon,
Yeah.
aren't they so stable that you can pass to the limit also with alpha going to minus 1 or 1 according to the two cases?
First, the result is, our result is false for alpha. Alpha is alpha or A?
Sorry, A.
Okay. The result is false for A equal minus 1.
No, but for even solutions also? Also
for even solutions.
Ah, okay, I lost this part then.
Okay. Yeah, the result is false in the sense that, okay, in the sense that when A is equal to minus 1, there are no energy solutions.
It depends on how you define the space of solutions.
No, you cannot. Energy solution with respect to the weight y to the A. Okay, so let's say something. If the result was true, constant solutions are not the solution when A. Constant solutions are energy solution because there are no even energy solutions when in the opposite class. In the other case, because when A is not integrable, You have, okay, let me say something. You have formal solutions for all ranges of A.
Okay.
This you can see.
In fact.
But in the case of a weight which is not integrable, these solutions are not energy solutions, right? Because the weight is not integrable. Okay, so maybe you can extend the theory and go also with, but then you extend the theory to the empty set, because there are no non-trivial energy solutions. So somehow the statement probably may be true, but it is useless because the even energy solution in the non-local integrable case are all constant.
Because they are even, but if you pass to non-even solutions,
the result is false.
Really?
Take any solution, then you can say this solution.
No, I mean, if you take the set of solutions, because I'm thinking about some related problems with the Grushin model in the parabolic case, in which you have solutions.
Okay.
Probably the space of solutions is different. This is the point. The energy space is different, probably.
The energy space is different for the Grushin.
Probably, I don't know. I don't remember exactly how it is defined.
If I'm not wrong, you multiply the square of the derivative with respect to some variable, you multiply them with by other variables.
Sorry, I didn't.
Grushin operator, if I'm not wrong, has a Dirichlet form, which is where the y derivatives are multiplied by the square of the x.
Yes.
Okay.
Yes.
Okay. So this is it's a bit different. This makes the energy space larger.
Yes, that's what I was saying. It's different. The situation probably is this one.
I don't know whether this type of analysis could be applied to the Grushin operator. Maybe yes, or at least one could try. Okay, but in this case, well, you take any solution and you divide it.
No, I see the point. Of course, I see.
Okay, so you take any solution. You have an odd one part and an even part.
Yes, no, it's clear. It's clear. It was just I was trying to see if there was a link, and if it was possible to pass to the limit somehow, or if you know how the constants.
My opinion, it may be possible to pass to the limit, but you don't find solution because
so the constant goes to zero.
Yeah, solutions are not there.
Yes, because the constant goes to zero. Okay.
In other cases where, in fact, maybe the energies, the requirement of being having a finite Dirichlet form is less restrictive than ours, then maybe you could find something. I don't know. I have not elaborated on the Grushin operator. In fact, this could be something worth some attention. In this particular case, simply you don't have energy solutions in the wrong.
Yes, of course. Yes,
of powers. But in fact, this is a particular fact.
Mm-hmm. Okay, thanks.
If you want, we can discuss another time.
Sure.
Haven't thought at all at other type of the generate operators, which are so hyperelliptic.
Okay, Paolo?
The question, okay, hoping not to disturb too much this deep discussion that you have. But Susanna, I am happy that you are working about regularity. I like very much this older continuity and higher regularity that you are doing now. I am just wondering, it is interesting this consideration of degenerate linear operators. And I remember a very interesting, classical paper by Trudinger in the 60s about linear and degenerate operators and the regularity for that. I wonder if there is any intersection with the results of Neil Trudinger with this new result that you presented today.
I'm afraid I don't know this paper you are mentioning, and I would be. What happens is that, and I have gone through the literature. The irregularity is a result of the combined effect of the operator and the boundary condition.
Okay, I see. In fact, I would read some details. If you give us if you have a preprint or something, a reference to point out, or either to send by email, I don't know. I will appreciate. If you like, I will send to you a reference of the paper by Neil Trudinger that could be of interest of you.
Yeah, thank you very much.
There is a difference. The regularity of Trudinger was interior regularity, you're right. And this is different what you are going to present. You are right.
This is, in fact, something very special, which is related to this cluster of operators, because, in fact, you do have polynomial solutions at any degree. Okay, even solutions are, you have an entire class of polynomial even solutions. And this is a key, because then you can approximate with the polynomials at any, as much as you want. So you basically find a Taylor formula, even though the coefficients of the equation are not infinite. They are sooner or later the derivatives of the coefficients are of the one coefficient. Let's say the y to the power y will do very bad things. But this is, in fact, a peculiar fact of this type of equations.
Thanks, Susanna. Do you already have a preprint or a reference for this research?
They have already appeared. Paolo, I will send you the slides, so you will find in the first page the references.
Okay. Thank you. In any case, it's not just for curiosity, scientific curiosity. I appreciate the seminar. Thank you.
Thank you.
Ian, please.
Congratulations for the nice talk. I have only one question. Do you have some results about Dini continuous coefficients?
About?
If the coefficients of the operators are Dini continuous.
Okay. As I said before, this result is tied to the particular form of the degeneracy. We know that the degeneracy or singularity will hold exactly at an hyperplane. So what we can say is let's take this class. We can look at the Dini continuity in two different ways. One is to take this class of weights, exactly these ones, and the matrix A, which is in front of the weight, take it only Dini continuous.
Yeah.
When A is continuous, we do have C0 alpha.
Yeah.
So maybe maybe we could go up to Lipschitz.
Yeah.
Okay. We haven't looked at the Lipschitz continuity. So we at this moment we have. I suspect yes, but because of the type of approach we have performed, Lipschitz. This is by scaling, which is our estimates by scaling. Is not so easy to get to have the limiting cases.
Yeah.
But maybe I also have to say that the C0 alpha part could be obtained by performing the analysis by Fabes, Koenig, and Serapioni. Which, however, doesn't give the exact exponent alpha. So it's somehow is a bit. If you want the exact exponent alpha, then you may pay a little bit on some other. Anyway, it's a very interesting factor, and I simply don't know. And even more difficult question could be, can you obtain C0 alpha estimates when the matrix A is not even continuous? Okay.
Yeah, of course.
No, I mean, these are just questions I am not. There is another point where continuity enters, which could be this other point of view. You may imagine that the exponent A itself depends on X. So somehow you may have points at the boundary where it has some value. Okay.
Yeah.
Okay. And this is also a very interesting question. We are working with Stefano Vita on this. And it appears that something can be done. So I don't know. There are, in fact, many limiting cases, and we simply don't have answers at this moment.
Yeah, of course. These are interesting questions. Thank you very much.
Sorry, probably you were thinking of A Dini continuous.
Yeah. To get some sort of Lipschitz continuity estimate, Lipschitz estimate for the solution.
This is also very
Maybe this limiting case in this sense. I don't know.
probably is very difficult.
Yeah. Thank you very much once again.
Thank you.
Some other questions? If not, many thanks again for this nice talk to Susanna and to all of you to be here.
Thank you very much for the invitation, and see you soon.
Grazie.
Ciao.
Ciao. Ciao
Susanna.
Grazie.
Ciao.
Ciao.
Raffaella also, and all the others. See you.
Bye bye.
Grazie per essere venuto, Paolo.
Bye.
Ciao Dimitri, ciao.
Ciao Patrizia.
Ciao.
Ciao a tutti.
Ciao, ciao, ciao.
Patrizia, ciao.
Buonasera a
Pomeriggio a
tutti.
tutti.